All right, since the PowerPoint has been posted on Chalk for quite a little while now, and all of you have had the time to look at the PowerPoint, do the reading, answer some questions according to our worksheets, we're going to start working on some of the examples and then some of the on your owns. Okay, so right now we're dealing mainly, we talked a little bit about inertia in our reading, and inertia means that things tend to continue on in the same direction and at the same speed as they were, as long as an outside force does not stop something from moving. Okay, so in other words, if you did not have friction and you rolled a ball across the gym floor, without friction, that ball would keep moving with the acceleration that you pushed it, and it would never ever stop. Okay, but friction is something that interrupts acceleration and movement. Okay, another thing is, say you're riding along and you are in a car and you are riding along at 70 miles per hour. Okay, if you hit something going 70 miles per hour and you are not seat belted, when you run into something going 70 miles per hour, your car may stop right here at the point of impact, but you are going to keep moving at 70 miles per hour, which is why seatbelts are so incredibly important. Because if you keep moving at 70 miles per hour, you are not going to be alive after hitting that wall, if that's what you run into, at 70 miles per hour, which is why seatbelts, again, are so incredibly important. So that's the law of inertia. Things will keep going in the direction and at the acceleration at which they were initiated unless something gets in its way and stops it. And that something to us is always friction. Okay, and we will deal with friction, and in Newton's laws, we have a whole bunch of specifics that will come into play when we start dealing with the second law in particular. And speaking of which, that's it. That is Newton's second law in equation form that says the sum, that's that strange looking thing there, the sum of the forces equals mass times acceleration. Mass will always be in kilograms. Acceleration will usually be in meters per second squared. And a force is always measured in newtons. Okay? Force has a label of newtons. Okay, so we're going to start using this equation in example 5.1, and we're on page 147. A person pushes a rock with an acceleration of 0.12 meters per second squared east. So there is our direction. Okay, if the rock has a mass of 4.2 times 10 to the fourth grams, and we'll convert that in just a second. Okay, what is the force that the person is exerting to move it? Okay, so mass has to be in kilograms. So the first thing we're going to do is expand 4.2 times 10 to the fourth by moving that decimal over 4 places to the right. So 1, 2, 3, 4. And then, of course, all of these get filled in as zeros. Okay, so we get that 4.2 times 10 to the fourth grams is 42,000 grams. Now we are going to make the conversion with the understanding that 1,000 grams is 1 kilogram. Okay, So if we divide 42,000 by 1,000, we are moving the decimal 3 places to the left to get 42 kilograms. And remember, the number of significant digits that we end with has to be the same as the number of significant digits that we started with. 4.2 times 10 to the fourth has 2 significant digits. Therefore, when we convert grams to kilograms, we need to end up with 2 significant digits in our kilograms as well. And here we've got it. Okay? Now, we are going to plug in F equals ma. Mass is 42. Acceleration is 0.12. And when you multiply 2 significant digits times 2 significant digits, your answer should have 2 significant digits in it. So when we do this multiplication, we get 5.04 newtons as our force. But we need 2 significant digits, so our force is 5.0. Okay, very basic, very simple to follow the main equation. Okay, now we're going to do 5.3 on your own. Okay, and we will forego 5.4 only because it's a concept question as opposed to a mathematical question. So on your own, 5.3, page 148, a man is pushing a car that has run out of gas. If he pushes with a force of 15 newtons, so there's our force, newtons west, and there's our direction. The car has a mass of 1.23 times 10 to the 6th grams. With what acceleration will he be able to push this car? Okay. Again, we've got grams for our mass, which is not going to cut it. So 1, 2, 3, and then we're going to move that decimal 6 places. So 1, 2, 3, 4, 5, 6. All these zeros now. And now we can convert those number of grams to kilograms. So that means that we are going to move that decimal point at the end of the last zero 3 places to the left. 1, 2, 3. So 1.23 times 10 to the 6th grams is the same thing as 1,230 kilograms. Now we started with 3 significant digits here in 1.23. So we need to end with 3 significant digits in kilograms, and we have them. Okay, so now we can plug in to F equals ma. The force is 15. The mass is 1,230 times acceleration. So when we divide both sides, we're dividing 2 significant digits on the top by 3 significant digits on the bottom. So our answer will have 2 significant digits. Now, what we get is this decimal, 0.012195, and it goes on. Now, we need 2 significant digits. So those first 2 numbers there are the first 2 significant. Actually, no, they're not, are they? That 0 there is not significant. Oops, boy, it's been a while. Okay, remember, this 0 here, because it doesn't have anything to the left of it, is not significant. So we are going to go out here. Those are the first 2 significant digits in the number 0.012195. So our acceleration is 0.012 meters per second squared to the west. Okay, and there's our direction. Okay? Now, the next equation that we see is on page 149, which is a weight equation. Okay? So if we compare that to force, force is equal to mass times acceleration. Now, weight, if you notice, the m in weight is the same thing as that m in the force equation. They are both masses. Okay? Gravity and acceleration can have the same value. It depends on if you are in free fall or not. Okay? And weight is also a type of force. So weight is also measured in newtons. Just like force is measured in newtons, weight is a force. Okay? And it is also measured in newtons. Okay? So in example 5.2, it says a man steps on a scale and determines that he weighs, his weight is 151 pounds, which is equivalent to 672 newtons. Okay. Determine the man's mass in both kilograms and slugs. Now, a slug is to weight like kilograms is, okay, let me rephrase that. A slug is a pound thing, whereas a kilogram is a newton thing. So, slug and pounds, then kilograms and newtons, okay? So a slug is the mass when you're talking about pounds. Kilograms is the mass when you're talking about newtons, okay? So if we've got a weight of 151 pounds, that is our force. So the mass then is a slug, so we're talking about pounds. Now, gravity, in terms of pounds, is 32 feet per second squared, okay? So we are in the American system when we talk about pounds, when we talk about slugs. Therefore, gravity has to be in terms of feet per second squared as opposed to meters per second squared. Now, if we wanted to do the same thing with F equals ma, 672 is our force, our mass will be in kilograms, and our acceleration is 9.8. Okay? So we would divide both sides over here by 32 to give you the mass in slugs, and we would divide both sides over here by 9.8 to give you the mass in kilograms. Okay? So 151 divided by 32 to two significant digits is 4.7 slugs. Isn't that just terrible? Now, if you did the same thing in newtons, dividing 672 by 9.8, you would end up with two significant digits, which would come out to 69 kilograms. Okay? So if 151 pounds is the same thing as 672 newtons, then 4.7 slugs is the same thing as 69 kilograms. Okay? Because the masses are the same if the weight and the force are the same. The weight and the number of newtons is the same. Okay? Now, in example 5.3, an object weighs 3.42 times 10 to the third pounds on Earth. So 3.42 times 10 to the third pounds on Earth. how many pounds will it weigh on the moon? Okay, and the acceleration due to gravity on the moon is, so acceleration on the moon is 5.3 feet per second squared. Okay. So, what we need to do, if we want to figure out how many pounds this thing will weigh on the moon, the thing that we need to understand and remember from the reading is no matter where you are ever in space, at the center of the earth, sitting where you're sitting at your desk, your mass will never change. The thing that is constant about you is your mass, okay? So if we use, actually we're going to be using weight equals mass times gravity, okay? So the weight that we are given is 3.42 times 10 to the third. That is the same thing as 3420 without the 10 to the third. That is the weight. Now again, the mass on Earth here is going to be the same thing as the mass over there on the moon. Gravity, when you're talking about pounds, is 32 feet per second squared. And when we divide 3420 by 32 to two significant digits, we get, first of all, we will get 106.875 is equal to the mass. And we need two significant digits there. So we're going to look at the very first two numbers. So the 6 is going to bump up that 0 to a 1. So two significant digits tells us that the mass is 110 slugs. Now that's the mass, and that is going to be the same whether you're in the classroom or on the moon. Okay, now we can find out what the weight is on the moon. Okay, so weight equals mass times gravity. The weight is what we are figuring, knowing our mass and knowing the gravity on the moon. So remember, no matter where you are, mass is always consistent and never changing. So 5.3 times 110 is 583, but we need two significant digits. So we're going to look at these two numbers and see, does that 3 change the 8? And no, it does not. So the weight on the moon, sorry, it's not in slugs, weight is in pounds. The weight on the moon is 580, and the weight on Earth was 3,420. So obviously, things weigh less on the moon because of the gravity being so much lower. Okay, now we are moving on to the On Your Own 5.5. And again, so far the equations that we are using are force equals mass times acceleration and measured in newtons, and weight is equal to mass times gravity, which is also measured in newtons. They are both forces. Okay, so what is the weight on Earth of a 13.5 gram object? Give your answer in newtons. Okay, so we have 13.5 grams. So first of all, if we're looking for weight, this is the equation that we are using. weight equals mass times gravity. But if you give your answer in newtons, our grams has to be in kilograms. So we have to convert that. Okay, so 13.5 grams. There are 1,000 grams in 1 kilogram. Okay, so we are going to divide 13.5 by 1,000, which is the same thing as moving your decimal 3 places to the left. So 13.5 grams is 0.0135 kilograms. Okay, and because we are giving our answer in newtons, our mass is 0.0135, and gravity in the metric system is 9.8. So we are going to multiply those two numbers together and then, of course, round to 2 significant digits. So that would be 0.0135 times 9.8. That gives us 0.1323. But we need 2 significant digits from that. So we're going to look to the very first 2 numbers there and decide if the 2 is going to change the 3, which of course it is not. So our weight is 0.13 newtons. Okay? And again, newtons goes with the metric system, 9.8, and pounds goes with the American system at 32. Okay? So that doesn't change at all. Gravity is still gravity. Okay. Now for the On Your Own 5.6. A Martian rock weighs 15 newtons on Mars. So let's write the equations that we need. Or let's just say the only equations that we know so far. Okay, things get much, much more difficult as we move forward with Newton's second law, but not quite so difficult yet. So a Martian rock weighs, so there's a weight, there's your force, 15 newtons. So the force is 15 newtons. How much will it weigh on Earth? Okay, now on the moon, or Mars, sorry, that's Martian, duh. On Mars, the gravity is 3.7 meters per second squared. Okay, so if something weighs 15 newtons on Earth, in order to figure out how much it, or let me rephrase, if a Martian rock weighs 15 newtons on Mars, we can figure out how much it weighs on Earth by figuring the mass. Because again, the mass of that rock is going to be the same whether it's on the Earth or it's on Mars. So we need to use W equals mg and solve for mass. So the weight on Mars is 15 newtons. The mass is what we are trying to find given an acceleration of 3.7. So 15 is 2 significant digits divided by 3.7, which is 2 significant digits. So our mass, here's the 0.054050, etc. And we need 2 significant digits. So the 5 is going to bump that 0 up to a 1. So the mass of the rock, regardless of where it is 4.1 kilograms. And we know it's in kilograms because our weight was given in newtons. So the mass is 4.1. Now we can find the weight on Earth by multiplying the mass times the gravity here on Earth in the metric system. Two significant digits when you multiply, you would get your weight as 40.18, and we need two significant digits out of that, okay? So these two numbers are the only ones that matter. But if we just write 40, the 0 is not significant. So we need to change that into scientific notation. 4.0 times 10 to the first is the same thing as 40. Because now that 0 there is a trailing 0 and it is now significant. So while 40 does not have two significant digits in it, 4.0 times 10 to the first does. Okay. So hopefully this is making sense as we're going through these practice or these example problems and the on your owns. Now the next thing we're talking about is normal force. So normal force is like, say you've got a man standing on the ground, okay? And this man has a specific weight, okay? So say the man weighs 180 pounds, okay? The floor that he's standing on is pushing back with an equal amount of force, so the man just stands right where he is. As long as his weight is not greater than what the floor can handle, he's going to stay right where he is, because the normal force and the weight oppose each other. So if we were drawing a free body diagram, okay, a free body diagram is basically using boxes and arrows. So say this was a mass, okay? Weight pushes down while normal force opposes it, okay? And as long as they are the same, then the object doesn't move up or down. Again, if the weight is greater than the normal force, in other words, if you're standing on a floor that's rotted and it can't hold you because your weight is greater than the force the floor can exert back on you, you will go crashing through the ground. But as long as the weight and the normal force are the same, there is no up or down movement of that box. It stays right where it is. Okay? So that's the idea of normal force. Normal force opposes weight. So normal force is equal to weight, but weight is negative, where normal force opposes it and is positive. So as long as the sum of those two forces is 0, in other words, if the normal force plus the weight, those are the sum of the forces, as long as the sum of those forces are equal to 0, the normal force is equal to the weight. And remember, gravity is a downward pull, hence the negative. Okay, so we're going to be looking at example 5.4. A 75 kilogram man stands on a level floor. So that is his mass, 75 kilograms. What is the normal force that the floor exerts on the man? Okay, well remember, normal force and weight oppose each other. Okay, weight is a force, and obviously normal force is a force. So mass is not a force. So in order to determine the normal force that the floor exerts back on the man, that equal and opposite force, we need to first figure out what the man weighs. So weight is equal to mass times gravity. And because we are given our mass in kilograms, our gravity is 9.8. And remember that weight is, I can't remember the word I'm looking for, affected by, but that's not the word, determined by gravity, which is negative. So when we find his weight, we multiply the 75 times the 9.8, and we get that his weight is 735 pounds, but we need two significant digits. So the 5 bumps up the 3, and his weight is 740 newtons, which pushes down. Okay? That means if weight is a downward thing, normal force is an upward thing. So as long as his weight is equal to the normal force of the floor, he's not going to fall through the floor, and he's also not going to get catapulted up into the ceiling. Okay? So 740 positive is the normal force, while the weight is 740 negative. Okay? So now let's look at, on your own, 5.7. Okay? A 3.8 slug woman stands on a step. That's a mass. In terms of pounds. Okay? What is the normal force exerted by the step? Well, her weight is going to be counteracted equal and evenly by the normal force. So in order to find the normal force, we have to find her weight. Now this time, because our mass is given in slugs, our gravity is going to be 32. So 32 times the 3.8 is 121.6. And we need two significant digits there. So we will keep the 1 and the 2, and that 1 becomes a 0. So her weight is 120 pounds. So she's exerting 120 pounds on the step. Therefore, the step is exerting back 120 pounds in the other direction, or positive. Okay? Very basic, quite simple. Now we're dealing with friction. Okay? And friction, again, is that thing that interrupts acceleration, especially when you consider Newton's first law, the law of inertia. Again, if you rolled a ball along a floor, that ball would keep rolling forever in the direction and at the acceleration with which you pushed it, but it eventually stops because of friction. So friction is a big thing that impedes movement. Okay? And we have static frictional force and kinetic frictional force. So static frictional force is the force that needs to overcome an object's friction as it is sitting still. Okay? When an object is sitting still, it has static friction. Kinetic friction is the friction that the object has when it is moving. Okay? So static friction and kinetic friction. Two different kinds of friction. Of course, think of when you're trying to push something really, 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 really heavy, okay? Trying to push it initially is much more difficult, but once you get it moving, keeping it moving is not so difficult, okay? And that's because of molecules, okay? So say we have this box sitting on a floor, a heavy box, okay? A very heavy box filled with 100 physics books, okay? You've got this box sitting on this floor, okay? The static frictional force between the floor and the box is very high. And that's because at a microscopic level, all of the atoms at the tiny level here, what is the word I'm looking? Again, words in my brain today are not clicking. On that really, really super tiny level here, you've got all of these atoms from the floor, right, fitting in very smoothly, closely, snugly, and tightly with all the atoms from the box. And that's the force that you have to overcome in order to get that box moving. So once you break up this tight accumulation of all the molecules and the floor together, you can start moving the box more smoothly and more quickly. Okay? So when the box is sitting here, it's experiencing static frictional force. Once you get the box moving, then you've got kinetic friction. There is some friction, but because the molecules between the box and the floor do not have time to readjust themselves and get all snuggly and cozy, the kinetic friction is a much less of a friction that you need to overcome to keep the box moving. And that's where we're going to stop today, so we can pick up with the coefficient of friction, static and kinetic, in further example and on your own problems.